All right, I'm here today to introduce some concepts of forces and to also talk about drawing free body diagrams. So the reason a free body diagram is called a free body diagram is because normally if we were to draw something, let's say this can of Zepp, try to draw something like this and Zepp and so forth, and that's complicated for me. I can't draw that very well. So I don't care about the object. I'm going to treat the object as a single point source or a dot. So that dot represents the body of the object as a single point in space. So it is free of the body itself. I don't have to draw that. We're going to treat it as a single point source. So that's why they're called free body diagrams. Certain types of forces that we'll think about in physics are things like applied forces, where you push on an object. We'll think of things like gravitational force, which always acts downward on an object. In this case, gravitational force we'll think of as always being caused by the Earth, and it acts to accelerate things down. In fact, it's a little more complicated than that, which we'll learn about later in the semester. We'll also think about frictional forces. So you listen to this, it scrapes along the surface. It slows down, that's due to an interaction with the surface. You can think of tension forces, where we have things like a rubber band, which is stretched. This might actually break, so let me do something a little stronger than that. So tension forces, such you would have in a rope or a string. Drag forces, such as air resistance, if it's present. We can have things also called normal forces. Normal forces is a general physics term for a perpendicular force acting on an object. So in this case, a normal force would be the table pushing up on the object. All right, let's go through and do some examples and draw some free body diagrams up here. I want to make sure you remember some of the rules we've talked about earlier. And this is from the bowling ball demonstrations. In general, we have no forces or balanced forces. We have no change in motion. An object at rest stays at rest. An object in motion stays in motion in the same direction at the same speed. If we have unbalanced forces, then that says an object's motion is changing. So we have a change in motion, and we call that an acceleration. If we have an acceleration, or a change in motion, that doesn't mean that the object actually has to be in motion at that instant, just that the motion is changing. So I'm going to be really careful to talk about changes in motion when we think about unbalanced forces. For example, if I toss this eraser up in the air, it reaches the tippy top of its path, and I'm trying to not throw it too tall to make sure it stays in the picture. At the tippy top of its path, it's no longer moving up, and it's not moving down yet. So we could say that at that instant in time, we've got zero motion. But obviously the motion's changing because it was going up less and less and less, and it comes down more and more and more. So at the tippy top, we've got zero motion, but we definitely still have a change in motion. And that makes sense because we have unbalanced forces acting on this object. In other words, the gravitational force is acting downward on the object. No other forces would be acting on it. So I'm going to use this can of Zepp 40 all-purpose cleaner as my example for a lot of things that we're going to be doing for a little bit. I'll try to make sure I draw my diagrams big, because I want you to see the table here, but at the same point, I want you to be able to see what's going on the board. So at this point, this can of Zepp is just sitting here. It's not very interesting. Well, what forces are acting on it? One force we can think of acting on that can of Zepp is the force of gravity acting downward. So I'll call that F gravity on Zepp. This is called an agent-object notation. The agent, or what's causing the force, is listed here. That's a gravitational force. Technically, it's the Earth, so you could say F Earth on Zepp. And the object that's being acted on is right here. That's the object. So F gravity on Zepp. Now, you might think that that's it. But if the only force is a downward force due to gravity on this can, it would be accelerating to the center of the Earth. at a pretty high rate. So there's got to be a force acting upward. Well, the only other force I can think about, the only thing that's interacting with this can of ZEP is the tabletop. So that's a normal force, but I'm going to label it specifically as force of the table on ZEP. Now, how big should it be? If I look at this, it's not moving, and more importantly, its motion isn't changing. So I've got to have balanced forces. So my force upward should be the same size as my force downward. So I'll say force of table on ZEP. When you have two forces that are the same magnitude, you can draw what's called a hash mark on those, indicating you mean them to be the same size. Even if you're not perfect at drawing the arrows the exact same size. So these are meant to be the same size. All right, let's go to another one. Let's say now we're thinking about this can of ZEP on the Cleveland Browns pillow. They're 5-2 right now. I probably won't ever get to say that the rest of my career. At any rate, say I put this ZEP on here. If you notice, it causes the pillow to deform. So a deformation or deformity or deformation in physics is not a pejorative term. In other words, it doesn't mean it's a bad thing. It means that the shape changes. That's all it means. So we have a deformation in the pillow. Believe it or not, we actually could have a deformation in the tabletop too, even though it's very hard to see it at a molecular level. So let's draw the free body diagram on this now. Well, if I look at it, I know gravity's acting down, and we don't know exactly what causes the amount of gravitational force yet. Probably it makes sense in some ways that this is going to depend on the amount of stuff that's in that can. But it should be the same as it was before. So I'm going to list this as F grav on ZEP. Now there's an upward force on the ZEP too. And the question is how much? A lot of times people want this to be less than the amount of gravity on the ZEP because they notice that there's been a pretty big deformation in that pillow. But if you look at it right now, the object's not in motion, and again, more importantly, it's not changing its motion right now. It was changing its motion as I was setting it down, but right now it's not. And so I've got to have the same amount of force upward on this, otherwise I would have the object's motion changing. So I'm going to say F pillow on ZEP. Now another question might come up is, what about the tabletop? Isn't the table acting on the ZEP? Actually, it's not. We want to keep things as simple as we can. For right now, we're only looking at the forces acting on that can of ZEP. For a long time, the only force we're going to think about that can act at a distance, in other words, when things aren't touching, is the gravitational force. The pillow is touching the ZEP, so it makes sense that it's pushing up. And you're right that the table has some effect on this whole situation, but really the tabletop is only acting on the pillow, and the pillow is acting on the ZEP. So the only thing that's touching this is the pillow, and that's why I've listed it here. If I wanted to do a different free body diagram about the forces on the pillow, that would be a different situation. The next thing is, I'm going to put the ZEP on the end of this meter stick. I'm pretty sure it's going to fall on the floor, but we'll see. Hopefully you'll be able to notice that as this goes off the end, it does begin tilting downward. It starts bouncing even. So we can see there's a deformation there as well. But once again, we would actually have the exact same free body diagram, because although the meter stick's deforming, it's not actually accelerating downward at this point. So I would say stick. If I let go of that, it's going to be a problem. So all three of those free body diagrams look the same. That's pretty boring, I understand that, but we want to introduce with pretty basic examples. The next series of examples I'm going to do are going to be a little more interesting, and so we'll go from there.